Wow, welcome to Instruction at Home. We're going to give this a try, a little experiment, see how it works. Feel free at any time to pause this, take down your notes. You can go back and re-look at something, especially the examples we'll go over. Sometimes that might help. You can even push a little further ahead, a little faster if that seems in order. We're going to start with operations with radical expressions, but it's been a while since we talked about simplifying excuse my handwriting, oh my goodness. Simplifying radical expressions. We ought to spend a little time doing that before we go forward. And excuse my use of the pen. Maybe I'll get better as time goes on here. Okay, simplifying radical expressions is what that is supposed to say. And we know quite a bit about it already. We knew it before you even got into Algebra 2. Let's talk about this very first piece here, roots. We're not going to talk about roots of quotients right now. We'll get to that in a few minutes. Just going to talk about roots in general. If I'm trying to find the square root of, let's say, 9, well, it isn't actually correct for me to say the square root of, is it? I need to say the square roots. Roots. Why am I doing that? Because I'm interested in both square roots. All squares have two square roots, don't they? The square root of 9 is only one of them. I need to think about not only this positive one, but also the negative one. That would be plus or minus 3. Or it could be written as plus 3 and minus 3. Although I wouldn't write it that way, would I? I would just write it as 3 and negative 3. There's a name we use for the positive root, and that's called the principal. The principal square root. What do we call this one then? This one is the negative square root. So anytime we're doing square roots, we've got a principal square root and a negative square root. Well, of course, another way we could define the principal square root is it's the positive square root. We've got to keep that in mind. That's going to come up for us soon. So this was easy enough, finding the square roots of 9. We know we've got the principal or positive and the negative. Suppose I was dealing with an unknown such as x, x squared. I'm asked to find the roots of x squared. All right, well, I'm going to take plus or minus the square root of x squared, which is going to be the positive value and the negative value. Now, there is a serious problem here. I'm not done yet. The serious problem is that I don't know whether x is positive or negative. X might be negative 3 for all I know. How can I assure that this is going to be a positive value, we know what to do with that. We have a operation in mathematics called the absolute value, which returns the positive value. And if I needed to do the negative value, here it is. So I just take the negative of the absolute. Anytime you're asked to find particular root, positive or negative, with a variable in it, you must be thinking about how do you make sure that the principal square root is positive. This only comes up when we've got a variable. All right. We're also going to be, we'll find roots of quotients. It's going to get a little more complicated. We know what a quotient is. We're going to divide one radical expression by another. And this is a fun one. This is one I really like, adding and subtracting. And this one, what is the important thing to remember? We cannot add or subtract terms unless they are like terms. And like terms means they have the same variables oh my goodness, my handwriting, and the same powers, okay? So there's a lot for us to think about just as we enter into this. We just did a quick review of finding roots. We're going to go on now to find roots of quotients. It'll get more interesting. Okay. Well, I said we're going to do roots of quotients. Let's just try simplifying a few things here before we get into that, because we may need a little practice. It's been a while. So we've got these two square roots, and notice they're both positive. And when I multiply them together, they remain positive, and I've got 3 times 12. It's perfectly acceptable, since they are both square roots, for me to combine them in this way. And that would be equal to the positive square root, the principal square root of 36, which we know, right? That's going to be 6. I had no variable here, so I didn't have to worry about any way this might go negative. Down here, I'm finding the square roots of a couple factors, 27 and a, my gosh, a3, a to the third, that aren't perfect squares, but they do have factors which are perfect squares. Okay, so I can figure this out. Instead of saying the square root of 27, I'm going to say the square root of 9 times the square root of 3. And instead of saying the square root of a cubed, I'm going to say the square root of a squared times the square root of a. Now, let's think about this for a minute. If a were, were negative, we would have a negative radicand. fix that a little bit. And for a square root, we know this doesn't have the 2 there, but we know that that's what it is. When there's no number there, we know it's a square root. If a were negative, then we would have a negative radicand, which would not be allowed. So one of the assumptions we have to make here is that a is either equal to or greater than 0. It's actually very helpful, because if I am able to make that assumption, then I don't have to deal with what if a were negative, okay? So we're going to just make that assumption clear. The square root of 9, we know, is a positive 3. And then we can't find the principal square root of 3. Well, we could, but it wouldn't be exact. So we're going to stay with exact, so we're going to leave that. And then the square root of a squared, where a is known to be non-negative, we can say is just a. We don't have to put the absolute value sign there. And the square root of a. Now that's pretty messy looking. We wouldn't write it like that. We would put the 3 and the a together, and we would put the square roots together, and we would write it as 3a, the square root of 3a. That's not particularly satisfying, but it is the correct answer. I should be boxing these when we get to the correct answer. Let me do it up here too. So there are a couple. Oh, we're just getting to the fun part here. Yes. Let me move this down a little bit so we can focus on it. Yikes. Do I have a perfect square here? Well, if I have a quadratic trinomial, 3 terms, the highest power is power of 2. So it's possible that this is a perfect square trinomial. If it is, then I get the very nice situation of being able to rewrite this as a square. So let's check it out. X squared, is that a perfect square? Yes, it is. The square root of x squared is going to be x. The square root of 49 will be, that's right, 7. And then what do I do with these? I multiply them together. So I have 7x, and I have to double it. Inside and outside, it happens twice if I have a perfect square trinomial. And this is good news. We've got 14x, which is just what we wanted for our middle term. So yes, we do have a perfect square trinomial. Let's take the square root of x. That becomes the first term in our binomial squared. Square root of 49, which is 7. And then to know the sign we're going to use, we always go to the same place, right here. We're going to use a positive. Now we're in good shape. Please notice that I am interested here in which root? The positive square root. So we've got equals the positive square root of x plus 7 squared, which would be x plus 7. The square and the square root cancel each other out, leaving us with this. Now we want to make sure we've got the positive root. What if x is negative 8? Uh-oh. That would give us a negative. So here's where we recognize we've got an unknown that could be negative. It could cause this whole expression to go negative, and we won't allow that because we are looking for the positive square root. Okay? Let's just go up and verify our answers here. Whoops. Oh, I'm sorry, I'm not that proficient. Maybe never will be. Okay, we're going to check that against what I did last summer. Yep, 6, it's a match. There's that messy one we didn't particularly care for. And maybe I should move this down a little bit so. And then this one. Okay. So we did all this. It's quite a bit to think about, eh? We did all this so that we could start to do quotients. We're going to apply the same thinking. First you're thinking about, okay, have I got a positive square root I'm looking for or a negative? Do I have squares in hiding? In the case of the second example we did, we had 9 hiding in 27, and we had a square hiding in a cubed. This one is even a better disguise, isn't it? It's a trinomial. Anytime you have that trinomial sitting there, be aware that it might be a perfect square trinomial. If it is, we can factor it. We can find that square root. Okay. Properties of exponents. Here are the rules we use. Whoops. Yeah, sure, that's the rules. Here are the rules we use. Or the properties that we apply as we try to work with these. These are very important. We already know them. If we have two factors that have the same base, to simplify them, we just add the exponents. If we have a divisor and a dividend, two parts of quotient, the numerator and the denominator, that have the same base, then we subtract the exponent that was in the denominator from the exponent in the numerator. That's the way we simplify that. And the power of a power, which obviously does have the same base, we have an expression, and then we're going to raise that still to another power. That's the only time you're multiplying. So these are our same base rules, and then we have a different situation over here. We've got two different factors, or if you look at it on this side, you might say two different bases. But what is the same? The exponent. And here, the exponent's the same, the bases are different. So this situation is where we have the same exponent. Now you might want to pause this for a moment at this point and write these down. It's going to be very useful to you. Okay, ready to move on. Finally, we get into what I promised you, that we would find the roots of quotients. We clearly have a quotient here, and it's probably pretty obvious to you that we've got a perfect square in the numerator and a perfect square in the denominator. So let's use one of our rules, which is as long as the base is the same, and this is square root, square root, square root, we can rewrite it as the square root of the numerator divided by the square root of the denominator. In this case, we can move ahead immediately because we know the square root of 4, it's 2, and the square root of 9 is 3. And of course, we were looking for the principal square root, so there we are. We're all set. We have a positive square root. How about this one? This one, oh, we're going to move away. We are definitely in Algebra 2. We're moving away from just doing square roots, and now we're going to be doing fourth roots. Let's apply the same practice here. We've got the square, the fourth root of 16 divided by the fourth root of x to the fourth. Oh, we're going to use stuff we were looking at earlier here. Now, in case the fourth root of 16 isn't obvious to you, there are ways you can use your calculator to help you out. Put 16 into your calculator, then use that upward caret, which the calculator will read as raised to the power of. Now, we're not raising it to the power of 4. Oh, far from it. We're raising it to the power of 1 divided by 4. So anytime you're doing the root, it's always going to be, when you're using your calculator and putting in the exponent, you put in this rational expression, 1 over whatever your root is. And what does that tell you? That's right. It's 2. Ooh, that's great. And we wanted positive. It is positive. Which means that I need to make sure that this is the positive fourth root of x. How can I do that? Because I don't know if x is positive or not. It might be a negative. It might be -3. I wanted to get a positive root here, clearly. So what do I need to do? That's right. Use my absolute value to make sure that I get a positive root. Down here, again, I'm being asked for the positive root. And I do see some perfect squares here. I'm going to give you a little hint for this one. Why don't we see if we can simplify within? That's a good idea. We'll simplify within the radical before we start doing much else. So we've got 8 over 4 times, times x over y squared. And that would simplify, of course. 8 divided by 4 is the square root of 2. And then I'd have the square root of x. And that's all over the square root of y squared. Oh, a square root of y squared is what? It's y. I can't do much about this. Whoops. I'll make this a little longer. We'll just put the 2x in here. Looks like it'd be a little neater than writing them separately. The square root of y squared is y. But I am stuck with that problem again, that I need to have the positive root. The only way to guarantee that is to take the absolute value. There I am. See if I can squeeze this one out over here. Oh, finally, an odd root. Up until now, we've been at least on this page, we've been dealing with even roots, square root, fourth root, square root. And of course, with those, we have to pay a lot of attention to keeping a root positive if it's asking for positive, or negative if it had been asking for negative. The good news is with an odd root, we don't have any of those concerns because odd roots can handle negatives. So we've got the fifth root, and every time I write this, I've got to put this 5 in here. Fifth root of 32 over the fifth root of 243 times the fifth root of a to the fifth over the fifth root. Oh, come on. I don't know why it's doing that, and I'll have to figure out how to stop it. B to the fifth. All right. Now, you might be wondering, why didn't I try dividing this all out at the beginning? For the same reason I didn't do that over here. Because I recognize that 32 is actually a perfect fifth root. Yes? You want to verify that. So put 32 into your calculator. Raise to the power of 1 divided by, that's right, 5. And what does that equal to? 2. How neat is that? And if you put 243 raised to the power of 1 over 5, this is one you might not be aware of, right? So it's good to have the calculator there, and it is actually a perfect fifth root. How nice is that? This is a beautiful little problem. So we've got 2 over 3, and those are positive roots, very nice. And we've got, we don't have to worry about positive and negative because we've got odd, right? We don't have to worry about that. So let me put in my A and my B. Because I've got odd, I don't have to worry about principal and negative. That's only something you're concerned with when you have an even root. Very nice. But I don't have to worry about that here. There's my answer. So, quotients. Radicals. Let's move on. Now, this is dividing radical expressions. There's some things we can do to make this a little easier. We use some of those rules. You have to be smart when you do it. You have to kind of look ahead and think, okay, what's going to work here? There's more than one way, but I'm going to try and show you the simplest way. In this case, you and I both see that if I divided 200 by 2, I would have a very nice number to work with. So I'm going to start here by, they're both square roots, so I've got the same exponent here. What is that exponent? It's actually 200 to the 1/2, that's its exponent, divided by 2 to the 1/2. We'll do more with that later. Okay, so they had the same root, same exponent. We could simplify, and now we're finding the positive square root of 100, which is 10. Very nice. And so much neater looking than the original expression. An odd root. Good. I don't have to worry about well, I don't have any variables anyway. It makes it easy. So I've got 7 times, and here I'm going to take the cube root of 81 divided by 3. Now, do you see why I'm doing that? Oh, this looks a little confusing. Let me do this. You see why I'm doing that? Because I recognize that 3 is not a perfect cube, 81 is not a perfect cube, but if I divided 81 by 3, what would I get? Let's do it. 7. The cube root, see, I'm having some problems here. Very aggravating. Cube root of 27. And the cube root of 27, of course you can do it on your calculator if it's going to come out even. It's very nice. It turns out to be 7 times 3, or the lovely 21. In our culture, that's an important age, isn't it? Okay, here we go with number 3. Oh my goodness. I think I'm going to divide it up like I did here. I'm going to put the numbers together. So we're going to have the 5th root. See how I have to look forward a little bit and think about what's going to work best? Because if I think about putting the numbers together, I'm going to get here the 5th root of 32. We saw that earlier. That's a nice 5th root. And then I'm going to do the a's. The a in the numerator was a squared, and the a in the denominator, a to the 7th. And then finally I'll do what I haven't done yet, the b's. b to the 6th divided by plain old b. Well, is it really plain? It sure looks it. We know that that's b to the 1st power. Just don't bother writing first powers. So I've got the 5th root. Oh, look what I forgot over here. I forgot to write in my little 5. I'm getting lazy. But that's important, isn't it? It makes a big difference. Okay, the 5th root of 32. And what's going to happen here? This will end up being the 5th root, don't forget that little 5, of 1 over a to the 5th. Right, it's a difference between these two, and we'll keep it in the denominator since that's the larger one. And the 5th root, I'm getting better, there it is, my little 5. And this is b to the 5th. I must be doing something to cause that to happen. I don't even know what it is. Oh, over 1. The 5th root of 32 we know is 2. And that's going to be over the 5th root of a to the 5th is a, and because it is an odd exponent, I don't have to worry about whether or not this is positive. And then I've got the 5th root of b to the 5th, which is b. I love working with the odd roots. They're so much easier. So dividing and simplifying. We use the properties of exponents there to help us get through to that and to get to some really beautiful simplifications. Now this is the fun part. adding and subtracting. What did we say up front we had to be aware of? We had to look for like terms. You're going to like this sheet, or maybe not. Maybe you'll find it boring. I think you'll like it because these are all like terms. So it's going to make it a little easier for us. So what are we adding here? We're adding the same thing. We're adding the square root of 3. So let's write that down. We're adding, I'm going to put it over here. You'll see why in a minute. Square root of 3. And now the question is, how many of those? Well, I've got 5 plus 4. So that's 9 square roots of 3. On this number 2, it's a little more complicated, the item that we're adding, but it's all the same, so we're in good shape. This is the cube root of 7. Oh, and I have to write that little 3 there. Sorry, it's not little enough. Equals, oh, don't forget that. And now I'm going to see how many of them I'm working with. I've got a 2, a positive 2. I'm adding 3. And I'm subtracting 1. Yes. We don't see the 1 written there, but we know that that represents 1. So let's see. That would be 5 minus 1, or 4 cube roots of 7. Very nice. And down here, wow, this is looking a little complicated, but it's still all the same expression. I'm going to write it out. This is the 4th root of 2x. And now we're going to see how many of those we're doing. We start with a negative 3. Then we add 8. And then we add 4. So we've got a negative 3 and a positive 12. We put those together and we get, let me put it down here. What do we get? 9 4th roots of 2x. I'm sure you will do much better in yours than I am doing in mine. I'm kind of sloppy with this electronic pen. We're moving on now to our last set of exercises. These are the ones that are really the fun exercises. I save them to last. What's fun about this? Well, remember, whenever we're adding and subtracting, radicals or anything for that matter, we can't add and subtract unless we have, that's right, like terms. These are not like. Oh, so I am in trouble here. However, if I look at the smallest component, which is the square root of 3, and then look at this, and I have to consider, is there anything I can do with this to convert it into a like term? That's what these exercises are all about, is trying to convert into, I'm going to move these two down a little bit so I have a little more space. Is there a way I can convert this 5, the square root of 12, into the square root of 3? Well, if I could factor out a 4 somehow, I would be in good business. Here we go. 4 times 3, which is the same as 5 times the square root of 4 times the square root of 3. See where we're headed, don't you? This is so great. 5 times 2, the square root of 4, times the square root of 3. So look what we've done. We've got 10 square roots of 3. We just converted this expression, plus, time for me to remember this. I've been ignoring the second term. I don't have to anymore. 2 the square root of 3. So I have like terms. I can add them together. My answer, 12 the square root of 3. These are like little puzzles that you solve. I hope you enjoy doing them. Oh, number 5. These certainly are not like terms. And yikes, do they share any common factors? See, the good news is that they are both the same root. That's a good thing. But I have to look to see if there's any way these can be simplified. You know, is there a perfect cube in here that I could factor out? No. So I can't do anything with that. Is there any way this one can become the cube root of 6? No, not using integers. It can't. It's a mess. There's no way I can do this one. No. So this one, we're going to say, cannot be simplified. And that's important to recognize, isn't it? You want to be wasting your time on something that can't be simplified. We've got plenty that can be. We want to move on to those. And let's do that now. Ooh. Well, we're going to use that same principle we used up here. Remember, up here we said, well, the smallest component is the square root of 3. So the smallest component here is the 4th root of 2x. Let me extend this page. The 4th root of 2x. So if I could somehow convert this fourth root, so I want to get this factored. I want to factor 2 out of that. So 2 times 16. Oh, this is looking very good, isn't it? 32, 2 times 16, and for this one, I'm going to say times x to the 4th times x. So now I've got my 2 and my x, which I was looking for. Let me rewrite it, make it a little easier to follow, perhaps. I'm going to take the 4th root of 16, it's this one, and the 4th root of x to the 4th, that one, and this is the one I want to simplify to, the 4th root. Notice how good I'm being. I keep remembering to put in that 4th root of 2x. I'm in business now, because what is the 4th root of 16? You probably know it by now. If you don't, you can take a minute and try it on your calculator. 16 raised to the power of 1/4 gives you 2. And then the 4th root of x to the 4th is, of course, going to be x, but I've got an even root, and I don't know whether x is positive or not. So I'm going to have to force it to be positive, because we are dealing up here with a positive root, right? I can't let it go negative. And then I will have the fourth root of 2x. I'm almost there. All I want to do here is simplify this a little bit. This would be 6, the absolute value of x, times the fourth root of 2x. Lovely! Now we can bring down this one, which we have been ignoring, plus 5, the fourth root of 2x. Oh, well, we managed this, didn't we? But somehow it's not all that satisfying. Why not? Because the 6, let me write it out, 6 absolute value of x is not a like term with 5. So that's about as good as we can get this one. That's our answer. And you are ready for our next class. We'll be working in class on doing some problems. See you soon.